Lesson 10H1, Using the PDAL Pipeline and ArcGIS Pro to create derivative elevation products. This lesson will cover how to create and implement a Point Data Abstraction Library, or PDAL pipeline script, that will generate derivative elevation rasters from USGS 3D Elevation Program, or 3DEP, point cloud source data taken from the USGS Entwine site. ArcGIS Pro version 2.8 will be used to visualize the data. However, any current version will work. The National Map is a collection of mapping products and services produced by the USGS National Geospatial Program. These products and services are accessible online at the National Geospatial Program website at usgs.gov/ngp. The National Geospatial Program has released a series of how-to videos for people who are working with the National Map data and services. The videos show how to use the services and interfaces to access data and tools for viewing, analyzing, and printing geospatial data. Lessons 1 and 2 serve as an introduction to the training materials, and the remaining how-to videos may be viewed as needed in any order depending on the user. The goal of the USGS 3D Elevation Program is to complete acquisition of nationwide LIDAR, IFSAR in Alaska, to provide the first ever national baseline of consistent, high-resolution topographic elevation data. Any use of trade, product, or firm names is for descriptive purposes only and does not imply endorsement by the U.S. government. By the end of this lesson, you will be able to install the open-source software PDAL and Miniconda to your local machine, utilize the command line window to create a Conda environment and call the PDAL pipeline, create and implement PDAL filters in a JSON-formatted pipeline to derive elevation products from Entwine point tile EPT point cloud source data, and visualize these products with ArcGIS Pro. For this lesson, you will be provided with a zip folder containing a LIDAR contractor report and pipeline JSON template files. Please download PDAL_training.zip from rockyweb.usgs.gov/training_data. The LIDAR data used in this lesson will access and process point cloud data from the USGS 3DEP repository organized as EPT resources. We will discuss this in greater detail later in this video. If you have not done so already, please download the data from the link provided. The National Map has a download client where you can find USGS products, including 3DEP elevation data such as LIDAR point clouds, at apps.nationalmap.gov/downloader. If you are interested in learning more about downloading products on the National Map, be sure to check out our training videos located at usgs.gov/ngp videos. After you've downloaded the data, extract the zip file into a folder on your local computer to use during the lesson. This tutorial will use a free minimal installer for Conda called Miniconda. It is a mini version of Anaconda that includes a handful of packages including Python and Conda. This also allows a user to install Anaconda packages separately to save time and space for what the user will need and use. The Miniconda installation file is located at docs.conda.io/en/latest/miniconda.html. Select the Python version 3.9 Miniconda 3 Windows 64-bit package under the Windows Installers heading. After the executable file has finished downloading, double-click the file and click through the installation steps. Agree to the license agreement. Choose Install for Just Me and the default register Miniconda 3 as my default Python 3.9. Finally, accept the default folder option and click Next and Install. Conda is an open source package for environment and package management created for Python programs. It assists with package installation and environment creation to run various versions of Python or software for any language. To learn more about Conda, go to docs.conda.io/projects/conda/en/latest. To begin, search for Anaconda in the Windows search bar at the bottom of the screen and open the Anaconda Prompt Miniconda 3 option. Conda is a versatile tool that allows the user to create custom environments for specific purposes. We will create a unique environment that will use the Point Data Abstraction Library, or PDAL, package to analyze and derive elevation data from the point cloud source data. Before we create a new environment, test the installed Conda package by typing conda --info in the command prompt and hit Enter. You will see information on your Conda installation. Now we will create a new environment named PDAL_tutorial. In the command prompt, type conda create-n PDAL_tutorial-y and hit Enter. The -n flag means new environment, and the -y flag accepts all the default prompts without pausing to ask the user to accept these prompts manually. Once the environment is created, it will need to be activated in the command prompt. Type conda activate PDAL_tutorial and hit Enter. Notice the base environment in parentheses has changed to the new PDAL_tutorial environment. Now the environment is ready for the PDAL installation. To install PDAL into the activated environment, in the command prompt type conda install-c conda-forge PDAL and hit Enter. When asked to proceed with the installation, type Y and hit Enter. This may take a few minutes. PDAL is a valuable library for translating and manipulating point cloud data. Similar to the Geospatial Data Abstraction Library, GDAL, handling of raster and vector data, PDAL can process point cloud data using readers, filters, and writers incorporated together as a pipeline. A pipeline defines an order of operations for processing data within PDAL and is represented as a JSON file using a key called pipeline. The structure of the pipeline uses an array of PDAL stage objects, which consist of strings of tags and inputs or other defined parameters in that stage object. A pipeline can be as simple as cropping a LAS file to a certain extent, or more complex like extracting only ground points to generate a bare earth digital elevation model, or DEM. PDAL readers provide dimension to the pipeline, meaning you can specify where your pipeline will access the point cloud data and the file type, such as this tutorial's readers.ept command. All point data in PDAL is stored as a set of dimensions such as the z-coordinate, classification, or intensity. Filters can remove, modify, or reorganize points from the source data by specifying wanted dimensions. Finally, writers consume the data provided by readers and will create a new output, such as a last tile or TIFF raster. More detailed information on PDAL can be found at PDAL.io. The USGS has created a 3-dep LIDAR point cloud repository at a USGS Entwine site located at usgs.entwine.io. This site uses an Amazon Web Service public dataset program to organize point cloud data as EPT resources. These EPT resources are streamable and lossless Octree-based LAS encoded files. Because of this Entwine repository, trillions of LIDAR point cloud records of LAS tiles, compressed to LAS files, are readily available for processing and retrieval in EPT format, or to be consumed by Cesium and Potree clients. After the installation is complete, ensure that PDAL is working on your machine by typing PDAL -drivers in the command prompt and hit enter. A list of the PDAL readers, writers, and filters should appear. Once you have briefly read over the PDAL drivers, we will change the network drive and make a new directory in the command prompt window. Type cd/d and insert the full path to the drive you want to use. Hit enter and the directory to the left of the command line should update to the directory and drive you specified. Next, create a new folder by typing mkdir PDAL_training and hit enter. The folder was created, but we will need to change the directory to the new folder. Change the directory once again by typing cd PDAL_training and hit enter. PDAL uses the concept of pipeline workflows to describe how point cloud data is processed, read, written, and filtered. Pipelines use a stream mode to process through the stages in order of succession. We will use a pipeline that will read the Entwine point tile, or EPT, surface feature points to generate bare earth and surface feature elevation rasters. From the results, we will construct an additional pipeline to generate a height above ground, HAG, elevation model. Now we will create the pipeline script. A template of the JSON array has been provided in the data download for reference called create_raster_template.json. Open the document using Notepad. In the File menu, click Save As. Navigate to your Conda working directory and make sure the encoding is set to UTF-8 at the bottom of the window. Name the file create_rasters_pipeline.json and click Save. In the create_rasters_pipeline.json file, we will fill in the blanks to create the PDAL pipeline. The first PDAL reader is readers.ept. This reader supports reading data from the EPT format by using a file name path and bounds to define the data source and extent. For the bounds parameter, enter the Web Mercator coordinates -119770004.545, -1197456.4.890 for the first parameter, minimum x and maximum x. In the next parameter, minimum y and maximum y, enter 4620226.461, 4622283.573. By defining this extent, we will only be selecting data from the point cloud located within the extent defined, rather than pulling every point within the work unit. Open your internet browser and open the USGS Entwine site located at usgs.entwine.io. A colorful map of the United States should appear, showing trillions of points from over 1,500 3DEP LIDAR work units. Each color represents a LIDAR project that has been published and made publicly available. Under the web map, click on the Filter box and type CO_West Central_2019. You will see the project filter on the map. Notice the 3 blue dots to the right of the table. Click on the EPT option and the EPT file will load in the browser window. This is the file name input that will be used in the pipeline script. Highlight and copy the link address of the ept.json file. In the create_rasters_pipeline.json file, paste the ept.json file link from the Internet browser to the file name parameter. Next, we will define the parameters for the filters.rangeFilter. This tool filters the input point cloud based on limits, or specified ranges for a given dimension. In this case, we will change the classification dimension of the point cloud to filter only ground points. Multiple limits can be defined using comma delineation. For the limits parameter, type classification bracket 2:2 bracket within the quotation marks. By specifying 2:2 as the classification range for this filter, only class 2, the ground point class, will be selected and displayed. The tag parameter enables the stage object of the reader, filter, or writer to be passed or cross-referenced to another stage. It is like a variable that can be used to carry previously defined parameters to the next stage of the pipeline. We will use the tag ground to define this stage as the filtered ground points. Type ground in the tag quotation marks. The next stage uses writers.las to create a las file from the previously defined filter. For the inputs parameter, within the quotation marks, type ground. Enter ground_points in the tag parameter. Using the writers.gdal writer, the pipeline will pass the ground filtered las file be_pointcloud.las to the GDAL raster writer. Name the file name be_raster.tiff and change the inputs parameter to the ground_points tag used previously. No data values are defined as -9999, and the bare earth raster will be calculated using an inverse distance weighting interpolation method. The resolution of the output bare earth raster will be 1 meter. The first section of the pipeline is finished. So far, the pipeline has defined the point cloud EPT source data file, created a boundary for all input points to be considered, and created a las file of only ground points. This las file is then passed to a raster writer that generates a 1 meter bare earth raster. The pipeline executes the code in successive order. Now we will repeat this same workflow to create a surface feature elevation raster, using more classification codes to include more points in the point cloud. The source file name, bounds, and type should remain the same as the first section of the pipeline. In the next section, referencing page 12 of the LIDAR contractor report, change the limits to classification bracket 1:6 bracket, comma classification bracket 8:17 bracket. This will filter all points from classes 1 through 6 and 8 through 17, omitting the low and high noise classes in the data. Name the tag surface_features. For the writers.las section, name the file name surface_features.las and use the surface_features tag for the inputs parameter. Name this tag surface_features_points. To create the surface features raster using the writers.gdal writer, name the file name surface_features_raster.tiff and type the surface_features_points tag for the inputs parameter. Leave the other default parameters. These are the same as the bare earth raster parameters. Save the pipeline. The raster generation pipeline is ready for processing. Back in the Miniconda command prompt, type PDAL pipeline create underscore rasters underscore pipeline.json -- debug and hit enter. This will take a few minutes. While the first pipeline is running, we will make a pipeline to create a height above ground raster that displays surface feature elevation values. In this pipeline, the height above ground Delaunay filter is used to create a new dimension of normalized height values called height above ground for a specified LAS file that contains a ground classification. Because we are using the LAS file format for point cloud data, various dimensions are stored as arrays in the data format, such as x, y, and z values. The filters.hag underscore Delaunay PDAL filter adds a new dimension to the LAS file, which needs to be isolated and passed down to the next stage to generate the correct normalized height values in the raster. PDAL has another filter that allows the user to overwrite the z elevation values and replace them with the height above ground dimension elevation values. By using the filters.ferry filter, we will extract the height above ground dimension and replace the existing z values in the LAS file. Open the dem underscore hag underscore template.json file from the data zip folder that was downloaded. You will see a series of empty quotation marks and blank sections to fill. Before the comma, underneath the first open bracket, type surface underscore features.las for the input file to be read and filtered by the pipeline. In the first stage, enclosed by curly brackets, type filters.hag underscore Delaunay. This filter will create the height above ground dimension that will be extracted in the next stage. In the next stage, inside the curly brackets, type filters.ferry. Then type dimensions : height above ground equals greater than symbol capital Z. The final stage of this pipeline will use the writers.gdal writer to create the height above ground raster. For the file name, type Delaunay underscore hag underscore max.tiff. Make the output type max to use only the maximum elevation values to be interpolated to create the raster. Finally, change the dimension to height above ground. Save the pipeline script in your working directory as dem underscore hag.json and close the pipeline JSON documents. Back in the Anaconda command prompt, type PDAL pipeline dem underscore hag.json -- debug and hit enter. This will run the first pipeline to create the LAS files and elevation rasters. While the pipeline is running, open ArcGIS Pro to visualize the rasters that were generated by the pipelines. This tutorial will use ArcGIS Pro 2.8, but any current version will work. In the New tab, select Map and name the project PDAL underscore pipeline underscore training and save the project to the PDAL directory used to store the pipeline files. In the Map Frame window, select the Map tab from the ribbon menu and click Add Data. In the Add Data window, navigate to your PDAL pipeline directory. You should see the ArcGIS Pro project folder, 3 rasters, and 2 LAS files. Add the Delaunay underscore hag underscore max.tiff raster to the map. Press OK if ArcGIS asks to build pyramids and calculate statistics. Right-click the Delaunay underscore hag underscore max.tiff layer and change the symbology color scheme to Inferno. Zoom into the left central area of the raster. Notice some building footprints. Click on the center of the dark purple building footprints to determine the heights of the buildings in meters. The stretch.pixel value is your height. Feel free to load and explore the other raster and point cloud tiles you created with the PDAL pipeline. Save the ArcGIS Pro project and exit out of the application. Close the Miniconda command console. Congratulations! You have finished Lesson 10H1, using the PDAL pipeline and ArcGIS Pro to create derivative elevation products. In this lesson, you learned how to install various open-source software such as PDAL and Miniconda, utilize the command line window to create a Conda environment and call the PDAL pipeline, and create and implement PDAL filters and commands in a JSON format pipeline to derive elevation products from 3D Entwine point tile point cloud source data. If you are interested in learning more about using LIDAR data, please see the 3D website at usgs.gov/3D and additional USGS training videos at usgs.gov/ngp videos.